Let's solve LeetCode number 42, trapping rainwater. In this question, we have been given an integer array height, where each element of the height array represents the height of the block at that particular index. The height of the block can be varying, but the width of the block is fixed of 1 unit each. We have to find the maximum possible water that can be trapped between any two consecutive pair of blocks. Let's take a real-life example to see how water works. Here I have taken two same containers with the same exact height and width. Now when it rains, these two containers fill up to their brim with the same amount of water. Notice the amount of water that is stored in both of these containers is determined by the left and the right boundaries of these containers. Now, if I were to break these containers at the exact same height, you will notice that some of the water flows out, both from the left container and the right container. Now, going one step further, you will notice that the remaining water is determined by the lower boundary out of my two existing boundaries. Here I have taken another container with the same dimensions, and it was also broken at the same exact point. The h-min here represents the height of the water left after the container was broken. Suppose this container had some of its space blocked by mud or sand. You will notice that the remaining amount of water that can be trapped in this container would be the minimum height of my boundary minus the amount of space blocked by that sand or the gravel. That is, h-min minus block would be my total available gap where my water can be stored. From the previous slides, we can gather three major points. The first one is that the highest left and the right boundaries of the container are responsible for trapping the water. The second point is that the lower boundary out of my highest left and highest right boundaries is the actual one which decides how much water can be trapped in that particular container. That is my deciding boundary. And the third and final point is that if some of my space is blocked in the container, then that also contributes to how much water can be trapped in that particular container. Taking a note of the previous points, one way of approaching this problem is by tracking the maximum left and the right boundaries for every single index. What we can do is, for each individual index, track the maximum left boundary and store them in the array, and similarly, we can track the maximum right boundary and store it in a separate array. Finally, we will loop through the entire height array and calculate the total water that can be trapped at every single index. Here I have taken a sample test case, and for this case what we will do is, we will keep track of the left maximum boundary and the right maximum boundary for each individual index. While we are doing that, we will also keep track of the height of the block present at each individual index to calculate the total water that can be trapped in the future. Let's go one step at a time. Initially, we are at 0th index. Here, our left maximum boundary is the same as the height of the block, because nothing exists before it. So, the left maximum boundary and the height of the block are both 1 unit each. Going one step further, at index 1, left maximum boundary still remains of 1 unit. But as there is no block present at the first index, the height of the block is 0. Going to the next index. At index 2, our left maximum boundary gets updated to a height of 2 units. And similarly, what we will do is, we will keep track of the left maximum and the height of the block till the end. And after this is done, what we will do is, we will run a second loop to find the right maximum boundary. This loop will start from the last index and go to our starting index. As it is starting from the last index to the first index, the loop will run in a reverse order. Now let me show you a cool thing. If we were to join our left maximum boundary and the right maximum boundary with the height of the block at each individual index, we will form specialized containers for every individual index. These containers depict how much total water it is possible to trap at that particular index. The left part of it depicts the left maximum boundary. The middle part shows the height of the block present at that particular index, and the rightmost part shows the right maximum boundary for that particular index. Now if you remember earlier, the total maximum water that can be trapped in any container is affected by the deciding boundary, that is the lower boundary of the container, and the total blocked space in that container. So what is the total water that we can trap at that index? That would be the minimum between my left and right boundaries minus the blocked space, that is the height of the block. Let's apply that logic for each individual index now. Starting from index 0, you will note that our left maximum boundary was 1 and right maximum boundary was 2. The minimum deciding boundary would be our left one, as it is of 1 unit only. At index 0, that would be 1 minus 1, the height of our block. That would be totally 0. Now going one step further. At index 1, you will notice that our left maximum boundary is 1 and right maximum boundary is 2. The deciding boundary is still the left one with a 1 unit height, and the height of the block at index 1 is 0. So how much total water we can trap there? That would be 1 minus 0, which is 1. We are capable of trapping 1 unit of water at index 1, as you can see both in the left diagram and our right container. Now going to the next index. In the next index, you will see that our left maximum boundary is 2 and right maximum boundary is also 2. Also, the height of our block at that point is also 2. Everything is 2. So the total maximum water that can be trapped at that point would be 2 minus 2, which is 0. Going to the next case. At index 3, you will note that the left boundary is 2 and the right boundary is 2. But the height of our block is 1. Hence, we can store 2 minus 1, which is 1 unit of water at index 3. At index 4, our left boundary is 2 and the right boundary is also 2. But the height of block is 0. There is no block present. So the total maximum water that we can trap would be 2 minus 0, which is 2. We can store a total of 2 units of water at index 4. Finally, going to the last index, that is index 5, our left boundary is 2 and the right boundary is also 2. With a height of 2 units, the block height is 2 units. So total water that can be trapped is 2 minus 2, which is 0. No water can be trapped at index 5. Thus, we have completed the whole traversal. The total water that can be trapped in the entire test case is 4 units. The arrows depict where exactly and how much water was found at every single index. The total time complexity of this entire operation is big O of n, because we are running a single loop from the start to the end of the height array with n elements. The space complexity whereas is big O of n. The reason being we are storing the left maximum boundaries and the right maximum boundaries in separate arrays. Each array would consist of n elements denoting the left maximum and the right maximum boundaries for every single index. Let us code the solution. Firstly, we will say that let L equals to the length of our height array. Then we will say that let L max be the left maximum boundary array for every single index. We will initialize this L max variable with the first element of the height array. That is because the first element is the starting element. And similarly, we will say let R max be the right maximum boundary for every single index. And that is initialized with the last element of the height array. Now, to find the left maximum boundary for every single index, we will run a loop in the range 1 to L, that is from the second element onwards, because we have already initialized the L max with our first element. What would be my new updated maximum left boundary? That would be the max between my previous boundary, that is L max minus 1, and the height of my current block, that is height I. Let us denote this by maxi. And what I will do is I will append this new maximum height to my Lmax array. That would be the maximum left boundary till that ith point. Now similarly, what we will do is to find the Rmax or the right maximum boundary for every single index, we will run a loop in the reversed order. This is because we had already initialized the Rmax with the last index, and that's why we are running the loop from the second last index to the first one. The maximum right boundary till the ith point would be the max between my previous Rmax boundary, that is Rmax minus 1, and my current height of my current block, which is height I. And I will append this maxi element to my right max array. Now till this point, I have found the left maximum boundaries and right maximum boundaries for every single index. Now what I will do is I will initialize a total variable, which is the total water that can be trapped for every single index. And to calculate that, for every single index, what I will say is the total water that I can trap at index I would be the minimum between my left maximum boundary and the right maximum boundary. The left maximum boundary would be my L max I, that is the left maximum boundary for the ith index, and the right maximum boundary would be R max L minus I minus 1. This is because we are going in a reverse order for the right maximum boundary. So once that is decided, the only thing remains would be taking the height of my current block into consideration. Finally, the total maximum water that we can trap on the ith index would be the minimum deciding boundary minus the height of that block, and that would be added to my total. Finally, after all of that is done, we simply return the total maximum water that we can trap at every single index. The total time complexity for this entire code is big O of 3n because we are running 3 loops to find all of our answers, but 3 into n simply becomes big O of n in the long run. That's why the time complexity is big O of n. Whereas the space complexity is big O of n because we are storing the left maximum boundaries for every single index, and similarly we are storing the right maximum boundaries for every single index. Hence there is a need to optimize this further. That optimization comes in the form of the two pointers algorithm. What we can do is, instead of running separate loops to calculate the left maximum boundary and the right maximum boundary, we can iteratively update the Lmax and the Rmax in one single go by using two separate pointers on the entire height array. Let's see how it can be done. Here is a sample test case. We will denote our left and right pointers with L and R. Initially, the left pointer starts at the first index, which is index 0, and the right pointer starts at the last index, which is index 9. While we are traversing this array, we will keep track of multiple things. Those are L and R, which are the left and right pointers, Lmax, which is the left maximum boundary till that point, Rmax, which is the right maximum boundary till that point, and the total water that can be trapped at any given moment. The total water that can be trapped would be our deciding boundary minus the height of the block at that moment. The deciding boundary is simply the minimum between our two current boundaries, Lmax and Rmax, and when we subtract the height of the block at the current moment, we get the total gap or the total water that can be trapped. Let's go one step at a time. Initially, our left and right pointers are at the 0th and the 9th index. Our Lmax or the left maximum boundary is initialized with 1 unit, which is the height of the block at the 0th index, and similarly the right maximum boundary Rmax is initialized with 2 units, which is the height of the block at the 9th index. Now here is a question. We have two possible options to go further. Either we can increment our left pointer to go in the forward direction, or we can decrement the right pointer to go in the backward direction. Which one should we choose? If you look closely at the Lmax and Rmax values, you will note that Lmax is 1 and Rmax is 2. The deciding boundary would be our left boundary because it is the minimum one. Now, what if I wanted to increase this threshold? Currently, I can only store a maximum of 1 unit of water, which is the Lmax value. What if I wanted to convert this into 2 units, which is the Rmax value? I would need to find a boundary higher than my current Rmax value, which is 2, for that to be possible. In that case, the roles would be reversed and Rmax would become the deciding boundary. In simpler words, I can say that I must traverse in the direction of my deciding boundary for me to find greater boundaries than my fixed boundary. Here, my deciding boundary currently is the Lmax and my fixed boundary is the Rmax. Because Lmax is less than Rmax, I must traverse in the direction of Lmax to find greater boundaries than my current Rmax value. So let's lay out some rules. If my Lmax value is less than my Rmax value, that means my left boundary is the deciding boundary, and hence I must traverse left to right to find a boundary greater than my right value. Hence, if Lmax is less than Rmax, we will simply go one step forward by doing L plus 1. On the other hand, if my right max value is less than my left max value, that would mean that my right max or the right boundary is my deciding boundary. And in that case, I would need to traverse in the right direction to left direction, that is right to left, to find a boundary greater than the current left value. And for that reason, we would simply decrement my current right pointer by 1. And the third case where Lmax and Rmax are both similar, we can give it to any version here, but I would choose to give it to the left max value. So if Lmax is less than equal to Rmax, we would increment our left pointer. Now let's go one step at a time to see how this algorithm works. To show you by the algorithm's perspective, I will hide the current block values so that you can see how this algorithm actually performs in the background. Initially, Lmax is 1 and Rmax is 2. Lmax is less than Rmax. So we will increment the left pointer one index forward. The left pointer goes to the first index. At the first index, the Lmax value still remains 1 by taking the max between the previous and the current value, and the Rmax also still remains 2 by updating the Rmax value. The total water that can be trapped at the first index would be the deciding boundary minus the height of the block. The deciding boundary is the minimum, which is 1, which is Lmax, minus the height of the block, which is 0. So 1 minus 0 is 1. We can trap 1 unit of water on the first index. Now going forward, my Lmax value is still less than the Rmax value. So I will increment my L pointer. Now when we go to index 2, Lmax value gets updated, but the Rmax value still remains same. The total water that can be trapped on index 2 would be the minimum, which is 2, minus the height of the block, which is also 2. 2 minus 2 is 0, so no water can be trapped on index 2. Now Lmax and Rmax are both equal to each other, which are 2 and 2. So by our law stated below, we will still increment the left pointer. Now we will reach index 3. At index 3, our Lmax value still remains 2 and Rmax value also remains 2. The total water that can be trapped, that would be my current deciding boundary, which is 2 minus the height of the block, which is 1. 2 minus 1 is 1, so we can trap a 1 unit of water at index 3. Now going forward, Lmax is still equal to Rmax, so we increase the left pointer. Now going to index 4. At index 4, we have Lmax equal to 2 and Rmax equal to 2. There is no block present. What is the water that can be trapped? That would be my deciding boundary, 2 minus the height of the block, which is 0. 2 minus 0 equals to 2. So we can trap 2 units of water at the fourth index. Now still my Lmax is equal to Rmax, so we will still increment the left pointer. Now left pointer becomes equal to 5. At the fifth index, my Lmax still remains equal to 2 and my Rmax still remains equal to 2. The total water that can be trapped would be equal to 2 minus 1, which is 1. We can trap a total of 1 unit of water at the fifth index. Similarly, like previous, Lmax equals to Rmax, so we increment the left pointer. Now at the sixth index, my Lmax gets updated to the value of 3. But my Rmax still remains at the value of 2. Now take a note here. Because my Lmax value has become greater than my Rmax, my deciding boundary has now shifted from Lmax to Rmax because it is the minimum one. And hence the roles have been reversed and so has the direction. So now we will shift from left to the right pointer. Now when we are going to the right pointer, currently the right pointer is at index 9. At index 9, my Lmax value is still 3 and Rmax value is still 2. What is the total water that can be trapped? That would be my deciding boundary, minimum of 3 and 2, which is 2, minus my current block height, which is also 2. So 2 minus 2 is 0, so no water can be trapped at the ninth index. Now take a note here. Lmax is equal to 3 and Rmax is equal to 2. My Rmax value is less than my Lmax value. Hence we decrement the right pointer by 1 unit. And the right pointer gets set to the 8th index. At 8th index, my Lmax value still remains 3 and Rmax value still remains 2. What is the total water that can be trapped? That would be 2 minus 1, which is equals to 1. we can trap a total of 1 unit of water at the 8th index. Now similarly like previous, Rmax is less than Lmax, so we decrement the right pointer. The right pointer gets set to 7, and the 7th index, Lmax is 3, Rmax is 2. The water that can be trapped is equals to 2 minus 2, which is 0. No water can be trapped. And finally, after all of this, my right pointer gets decremented to index 6, where my left pointer was originally left. Since our left and right pointers are now at the same index, we stop the iteration. Now if we take a note of the total water that can be trapped, you will see that a total of 6 units of water were trapped at the following indices. A fun fact about this algorithm is that no matter where you start from, this algorithm will always end the left and right pointers on the highest block of the entire array. This is because we are traversing while comparing the left max and the right max, and it can only stop when we achieve the greatest possible trapping sequence. Now this entire code would take a total of big O of n time complexity because we are traversing the entire height array using the left and right pointers, and the height array contains n elements. That's why time complexity is big O of n. But the most important point, which is the space complexity, is constant or big O of 1. The reason being we are just using two variables, which is the Lmax and Rmax, to iteratively update them during our traversal, and hence no extra memory to store each individual index and their boundaries is required. Let's code the two-pointer algorithm. Initially, we will initialize our left and right pointers by saying L equals to 0 and R equals to the last index, which is the length of height minus 1. Then we will say that our left maximum boundary is initialized with the first element of the height array. And similarly, our right maximum boundary would be the last element of that array. Then we will also initialize the total, which is the total maximum water that can be trapped. Then we will run a while loop which runs till the left pointer is less than the right pointer. In this, we check the first condition, that is the left maximum boundary less than equal to the right maximum boundary. That would mean that my Lmax is the deciding boundary and we need to traverse from left to right direction. Here I will add the total water that can be trapped for this particular index. That would be total plus equal to my minimum deciding boundary, that is Lmax, minus the height of the block at that index, which is height L. After that, what remains is we will increment the left pointer to L plus 1 and update the maximum Lmax value, which would be the maximum between my previous Lmax value and the block height of my current block. Similarly, if my Lmax was greater than my Rmax, that would come in the else statement, and that would mean that my right maximum is my deciding boundary. And for that reason, we would add total plus equal to Rmax minus the height at the right pointer. Then all that remains is we would decrement the right pointer by 1, that is R minus equal to 1. Then we would also need to update the Rmax value, which is the right maximum boundary, by taking the maximum between the previous Rmax value and the height of the block present at the new updated rth pointer. That would be height R. After all of this has been done, we will finally arrive at the state where the left and the right pointers are at the same exact index, the index with the highest maximum height, and then we will simply return the total maximum water we had trapped along the way. The total time complexity of this entire code is big O of n because we are running a single traversal using two pointers, which are the left and the right pointer, on n elements of the height array. Whereas the space complexity is constant or big O of 1 because we are just using two initialized variables, which are the Lmax Rmax, to find the total maximum water at every single index. Now, when we submit this two-pointer approach code for all the possible test cases, you will see that there is a great optimization in both runtime and memory, which is the main focus, is just big O of 1, which is constant in nature. That's it for this video guys. Thank you so much for watching and I will see you in the next one.